Okay, welcome everyone, and thank you for joining us for today's webinar. My name is Laura Roberts, and I'm the Ava Marketing Manager at PDS Group. For those of you who may not be familiar with PDS Ava, we build cloud-hosted software which addresses key limitations in existing reservoir modeling workflows. In today's session, Victoria O'Connor, Ava Director Geoscience International, will explore how you can bring analogues into reservoir facies modeling workflows using Ava Clastics. We'll start today's session off with a little housekeeping and then jump straight into discussing why, despite it being best practice, it's still a challenge to incorporate analogues into reservoir models. Using the Kapuni field as a case study, Vicky will show you how Ava Clastics can help you seamlessly incorporate analogues in your reservoir models. Before we get started, if you do have any questions during the presentation, please type them in the question box in your GoToWebinar control panel. Vicky is more than happy to answer questions throughout the session. We'll also allocate some time at the end of the webinar for questions and a discussion. If you wish to ask questions then, you can again type them in the question box in your control panel, or alternatively, if your question requires a little more explanation, use the raised hand function and I'll turn on your microphone so you can ask the question verbally instead. So now, without further ado, we will turn the time over to Vicky. Vicky oversees the product commercialization of PDS's geoscience e-services. She holds an MSc in geoscience from the University of Liverpool and has over 10 years experience in the oil and gas industry. Take it away, Vicky.
Oh, thank you very much, Laura. I hope you can hear me okay.
Yes, I can.
Wonderful. Okay, let's get started then. So, yeah, thanks for the introduction there, and thank you all for taking the time to join us today. I know people have got very busy schedules, so yeah, really appreciate your time to come and join us today. So I just want to kind of do a couple of slides up front, and then we'll take a look at PDS Ava Clastics and how that works in the Patrol platform using the case study that Laura mentioned. So we'll start off by looking at kind of a topic that's kind of interesting to me in general, and that's this kind of conceptual problem around how we actually deal with analogues in reservoir modeling. So just to check that everyone's awake and kind of able to use their controls, we're going to run a quick poll, and I'm going to ask you basically, you know, what do you think, before we get into the discussion, what do you think is the kind of the key problem in applying sedimentological analogues to or in reservoir modeling workflows? So Laura's going to run a poll, and you should see something appear on your screen, and you can pick from one of the options and then make a choice. Okay, I guess we probably have a couple of votes there, Laura, or?
Yes, we do. Pretty much everyone's voted.
Excellent.
And it's a split between increasing analog data quality and other. So perhaps in the discussion time at the end of the session, we could explore what exactly people meant by other.
Interesting. Well, I would certainly be interested to hear what you have to say there, guys. So do feel free to type in the question box with your comments, as Laura says there. But just to kind of give you sort of my perspective, I guess, and there are some challenges which when we go out and we talk to our clients, they come up time and time again. So I've got 5 kind of general challenges that I think are kind of there and are quite pervasive when we're thinking about how to accurately and intelligently apply geological analog information to basically counterbalance the sparsity and the locational bias that we have based on just the well data. So firstly, and this is a kind of a philosophical one, is definition. So what actually makes a suitable analog? What do we mean by analog? These are kind of questions that come up always at the start of every discussion. Are we talking about a particular outcrop? Are we talking about a range of outcrops? You know, do we need more than one outcrop or one analog to actually, you know, form the basis of our workflow here? So it's kind of a philosophical one, but defining actually what we mean by analog is quite important, I think. Moving on from that, I think something I would refer to as richness is a second point. So there are quite a lot of, you know, sort of analog data sources out there in inverted commas. But what we really need in order to actually apply analogues to reservoir modeling sort of workflows and actually link them up with things like Facies modeling algorithms is ensure that those analogues are actually rich enough. So do they actually contain the right type of geometric and other supporting data to actually be useful when we connect them up and try and apply them in our workflows. So something we'll come back to in a minute. But yeah, it's basically about whether the available analogues have enough data and enough richness in that data to actually be useful. Thirdly, I'd say there's an issue with breadth. So quite often people ask us, well, it's fine, we might have a database for X and Y, but it doesn't really cover the range of depositional environments that we believe to be there in the subsurface. So yeah, you definitely need access to data or databases that cover that broad range of depositional environments to really be useful, I think. Fourth is efficiency. So particularly when I speak to geomodelers about how they take analog data in their current workflows, maybe from papers or in-house databases, there's definitely always a discussion around the way they do it now, which in many cases is quite manual, kind of slow. There's sort of manual calculation steps involved, and actually converting the analog data itself that's available to them into the inputs required for Facies modeling algorithms is quite a challenge. So people kind of often bring efficiency up as a bit of a barrier, and that's often a barrier to trying out multiple analogues in their workflows as well. And finally, auditability. So one of the key sort of feedback we hear from more senior geologists, sort of the discipline leads and people like that, is that it's quite challenging for them to, they're approaching their teams and they're saying, hey guys, which analog or range of analogues have you used in this workflow? And having some ability to actually audit the analog or analogues that are selected and the work steps taken to transform that information into the Facies modeling sort of workflow in this case and express that whole audit trail is kind of missing. So yeah, auditability is a big one, particularly at a company kind of level. So how do we kind of address some of these problems and how are we starting to tackle them with this product, Overclastics? So I'll give you a quick overview of the product now, and I'll introduce the case study, and then we'll take a look live inside the product. But just to give you a background here, PDS Group and the University of Leeds work together to deliver this Overclastics technology. So the University of Leeds, based here in the UK, have a really strong sedimentological research group. There's around 50 sedimentologists working there at the moment, and they work in a range of different depositional settings, and one of their major topics of research for the last 10 plus years is in this area of databasing. So across the different research groups, they look at fluvial, shallow marine and deep marine settings, or deep water settings, I should be more specific there. But they cover this kind of broad range of depositional settings, and they've been building databases over these years that actually describe the key parameters of those different environments as well. So they create some quite well-established databases which are described in the literature covering these different environments. And that's what we bring to our clients through this Overclastics platform. And really our goal with Overclastics is to provide a kind of a single point of access to these data sources and potentially other databases as well, proprietary or public, but provide a single point of access for people to explore the data contained within them, represent that in a variety of different ways visually, and then analyze it in a structured way so that they can then take that analog information and apply it in whichever reservoir modeling platform they happen to be using at the time. So I use this in the third bullet there, I use this term, the depositional concept, which won't mean too much at the moment, but you'll see how we use it as we go through. But the idea is that we create what we call a depositional concept, which is a query of one of these databases paired with the settings extracted from that query, which can then be applied directly into a Facies modeling algorithm. So you'll see that working in practice in a few minutes. So we have a quick case study here just to kind of go through, and I guess it'll probably take about 15, 20 minutes, something like that, to kind of go through all this. But I'm just going to introduce the Kapuni case study. So this is an onshore field in the Taranaki Basin, North Island, New Zealand. It's discovered in the late 50s and has been producing since the early 60s. And it's quite an interesting, established mature field. And there's around 15 or 16 wells across the area. It's a really nice set of data, and if anyone happens to be interested, this data release is from the New Zealand government, and they have a huge range of really nice, high quality, publicly available data sets, and this is just one of them. So that's just FYI if you're interested in that kind of thing. But what we'll do is basically going to go through a quick workflow to show you. So going to give you a feel of how Ava works. So I'm going to take you into Ava, and I'm going to use the version of Ava that's embedded inside Petrel in this case. So there's a standalone area, web browser version, and then there's a version that's embedded inside Petrel, and that's the one we're going to look at today. What we're going to do is pick one of the databases, and in this case we'll use the Fluvial one. And I'm just going to show you how you can explore the data and build up a query of that data, and then bring that query into this thing called a depositional concept. So store that query and the expected proportions and the geometries that we expect to see from that particular query, and then take that analog data and basically convert it and apply it into the inputs required for Facies modeling. So you'll see how we go from just visualizing the data in the database right through to the results that you can achieve by effectively applying this analog through, in this case, through Petrel. And you'll see that as we do that, we honor the upscaled cells as well. So we're tying to the well data, but we're using that analog to inform the uncertainty in the interwell space. Okay, so let's jump into Petrel. So hopefully everybody on the call is at least familiar with how Petrel looks. But just to give you some background again, so this is the Kapuni field. We're just looking from the southeast in this case at one of our seismic horizons. You can see the fault, a major structure running north-south. There we go, running north-south down the side of the field. And this is actually a fairly simple geometry, so just a four-way closure essentially in the hanging wall of a major structure. There are some crestal faults as well, but we haven't actually modelled them for the purposes of this exercise. But you can see the well locations as well, kind of nicely spread across the field there. Okay, so this is just kind of standard normal work. What we've also done is we've taken a look at the well logs. So these are just a selection of wells across Kapuni, and you can see some of the logs there and the associated interpretations. And basically what we've done is interpreted 4 different facies from the well logs. So we have a channel, an overbank, a background, and some coals as well. You can see the coals quite clearly there in the logs. So we've gone through, identified 4 distinct facies units, and you can see those represented in the colours there. And what we've of course done is taken them and upscaled them into our 3D grid. So just a standard workflow that people are very used to. So you can see the layering that we've selected there as well. So let me just show you that in 3D. So if I turn off the top horizon, and we'll just turn on the upscale cells, so you can see some of those there as well. Okie dokie. So let's now start to use Ava to kind of inform the property distribution between the wells. So it's fairly straightforward. You come into the Ava tab, and we've got a couple of different products, but today we're just looking at Ava Clastics specifically. And as I come into Ava, you'll notice that it says my name at the top of here. That's because Ava is personalized. All our Ava products run a little bit like this in some level of personalization. So I log in, and this window, this custom window that I've opened in Petrel, takes me directly to a web environment hosted by us here at PDS, which is kind of neat and a little bit different from normal plugins that you see. It's a little bit of a different way of deploying it, but the reason we've done this is so that we can seamlessly update this anytime we like. So the databases that I mentioned from Leeds are constantly growing. So every 2 months we release new versions of these growing databases, and we can automatically update Ava here for you on the screen without you having to do anything. So it's kind of neat. So we're on the first page here in Overclastics, and it's just some background material basically. So here we've got some videos that kind of show you how that all works, and we have some links to some resources as well. So things like linking to some of the leads websites. You can re-download the installer for someone else, that kind of thing. Okay, so let's run through the workflow now. So there's 3 steps I'm basically going to show you pretty quickly so we don't run out of time. But essentially there's 3 steps. So there's this first sort of area, which is the Explore Analogues area. So we'll start here, and we'll spend a bit of time kind of looking at this one in particular. Then there's this depositional concept thing, which I kept referring to in the presentation, and we'll take you through one of those as an example. And then there's the modeling step, where we actually take that depositional concept that contains the query of the database, and we'll kind of use that to create a property here in our 3D grid. Okay, so on the screen here you can see the explore area, so that's kind of step 1 of 3. And as I mentioned, we have different databases. So we have these strange acronyms, but SMAC stands for Shallow Marine Architecture Knowledge Store. So it's a shallow marine database. And here you can see some of the data from that. Again, we have the deep marine one as well, which will be actually coming out for commercial release in the next few months. But we'll just jump back to the facts, the fluvial one just for now. And I'm just going to show you a couple of different visualization options that we have, which I think are kind of neat. So on the screen here, it's just a standard cross plot. So this isn't anything too exciting, and it looks quite crowded and the data is kind of overlapping because we are looking at all the data in the database at this point. That's why the floodplains and channels are all kind of overlapping. But one of the things I didn't mention in the presentation, and I'll comment on now, is that one of the neat things about these databases is that they are on different scales. So we're looking here at the depositional scale. So this is the largest scale in these databases. So we're looking at, in this case, in facts, the depositional scale, which is basically channel complexes and floodplains, so the big scale stuff, seismic scale stuff. But there are other scales here too. So there's the architectural scale and also the Facies scale as well. But we'll just look at the architectural scale for now. So these are objects between kind of tens and hundreds of meters. So I'll just show you a couple of options here. So this is just a cross plot, just like we were seeing previously. And you can see all the different types of elements here. So abandoned channel fills, overbank fines, levees, that sort of thing. And we have a few different types of options for representing this kind of data. I'll just show a couple. So here's the box plot. So again, this is the kind of representation that you see fairly often in the literature when people are referring to these kind of systems. And this is all customizable. There's all sorts of different ways you can flip around the axis and stuff, but that's not necessary for the moment. Pie charts, histograms. I'm just going to show you the transition chart, which people kind of get a little bit excited about. So another thing that's kind of really special about these particular databases is that they contain some statistics on the neighboring elements. So which particular element is next to what other element at a given scale. So let me just kind of explain that a little bit more clearly. So here, for example, we are presented with a whole list of the different architectural elements. So this is the middle scale of the database. And if I just look at one, in this case, the abandoned channel fill, then what this graphic is representing is the likelihood, basically, of encountering a different the same or a different element in a given direction. So if I just click on this one here, so this is the lateral option. So this is saying laterally from an abandoned channel fill, what am I likely to encounter? Bear in mind, this is all the data in the database right now. But this is saying that you're fairly likely to encounter either an aggradational channel fill element or a laterally recruiting macroform. Okay. So that's kind of where we are. And of course, as we start to apply filters and explore the data, this kind of changes. But just for simplicity, I'm going to go back to the depositional element scale. So back up to the larger scale in the database. And we'll just go back to that cross plot as well, just to make things simpler. Okay, right. So now we've seen there's different visualization options. Now we're going to take a look at applying a couple of filters. So if I have some information that kind of indicates that perhaps I'm in a certain depositional setting or a certain paleoclimate or age or whatever, I can start looking through the filters that are available to me from the database and start building up a query of that particular database. So that's what we'll do now. So in this case, I'll just apply a couple of simple filters around the depositional setting. And in this case, I'll just use paleoclimate, just to kind of give you a sense of how it works. And obviously, as we do that, the data starts to filter. Okay, so we've constructed a query. It's a bit quick, but that's all fine. If we wanted to, we could also go ahead and look at the studies as well. So it's possible to look at where this data actually derives from as well. And it's a combination of published literature and field work that's been done by the team at Leeds as well. So we get to this point and we've finished querying. Now we're going to move on to step 2, which is this depositional concept term that I keep referring to. So we're going to build one of these depositional concepts now. Okay, so there's basically 2 elements to this. I just need to give it some form of name. Okay, it's not very exciting, but that'll do. So just give it a name, and because we just saved that query effectively, you've got a recap of the information. So that's just the same crossplot that we saw previously. So we store the analog data associated with that query in this section here, so you can revisit it. And that's kind of one half of the depositional concept. The other half is actually expressing that subset of information in sort of the settings required to actually drive a Facies modeling algorithm. So that's what I'll show you in this step now. So the second half of the depositional concept is taking that analog data and on the fly processing it, ready to deliver into a Facies modeling algorithm. So I'm going to model on the depositional element scale, the large scale. And as soon as I make that selection, you'll see that the form starts to grow. So immediately Ava's saying, okay, you want to model the depositional element scale. Okay, tell me what you want to model. And by the way, these are the proportions that we see in this particular system, in this case, a coastal plain humid setting. So we're expecting to see something along these lines. If I was modeling at the architectural element scale, I'd be presented with slightly different options because there are additional element types within that particular setting. But we'll just do the depositional element one for now. So I have to make another choice now. So I have to say, okay, I'd like to express my analog using a particular modeling algorithm. And for the fluvial setting or FACS database specifically, we've currently enabled 2 algorithms, object-based modeling and sequential indicator simulation, which will kind of, based on feedback from our clients, they're the 2 that people are kind of using predominantly in these settings at the moment. But of course, we can add more as we go through time. So if I were to select sequential indicator, just to give you a flavor there, and I have to now tell it that I want to model channels and floodplains. So I'll just select those. And as I switch between different algorithms, on the fly, we're using a logic to convert that analog information directly into, in this case, variogram ranges. Okay. But if I switch from SIS back to object modeling, you'll see below that these tabs have changed. And in this case, we're now looking and we're directly extracting, in this case, amplitude and wavelength, thickness and width. So we're doing these calculations on the fly and giving you some recommended inputs basically for these algorithms. Now, this is our logic, and you may decide you wish to change it for whatever reason. If you do, you can. So we don't lock you down to this particular series of settings, but what we do is preserve your change alongside the original settings. So the green line is what we had as a sort of the intelligent default, and the blue line is the distribution that you've checked on as an override. And this is important and interesting because one of the options that we offer is the ability to report this all out. So you can export the whole form, this whole audit trail around the analog you've selected and the settings that we've derived from the databases. You can export them as a PDF, so you can hand them to a reviewer, for example. Okay, so we go through this process. I'll just save what I've done at this point. And we also have things like a log and stuff in here as well, which show those changes over time. So you can come back and revisit these concepts time and time again. But that was just a look at one depositional concept. So that's what you see here. Oh, it's a little error. It's strange. Must have changed the setting. But you can see that there are a whole bunch of different ones. So we've created one here for the settings that we just, the query that we just created. But I had a bunch that I made previously as well. So you can build up a whole series of these. And because it's all personalized, as I mentioned at the start, it knows who's modified them and when, which database was used, which scale is used, which modeling algorithm is used, stuff like that. So it records your work in that way. Okay, so you build up a depositional concept in the way I've just described, and ideally, hopefully, you develop a couple of different alternative ones, so you can test some uncertainty in your analog selection. And then what we have to do is connect them up with an algorithm and apply it directly. So we've selected the analog, we've selected a Facies modeling algorithm. Now we have to say apply that to a certain grid in our Facies model, in our 3D grid in Patrol, basically. So you select a particular grid. In this case, I only have one, so it's kind of easy. I can create a new property, or I can update an existing one if I have upscale cells. I'll just run you through this quickly so you can see how it works. There's a property template here, so if you have a certain property template you'd like to use, you can do that. But just to go through this reasonably quickly, we have another option here where you can apply different depositional concepts to different zones in the model as well. So I'm just going to, for sake of time, just select a single depositional concept for all zones. So let's go for that one, I guess. One I made earlier. So what this is saying is that I'm going to apply the same depositional concept to all zones in the grid. Now, we've enabled it this way because there may be some, for example, some vertical change. You may want to use a different depositional concept to represent a different zone vertically. So that's why we've done it this way. So you can choose different DCs for different zones. And then finally, you have to just tell Ava that in this case, a channel complex is mapped to a certain element in the template. Okay, and then you're ready to go basically. So I've just clicked apply modeling parameters and it says modeling settings applied. I'm just going to jump back. It's a bit strange because it's on a single screen, but we just jump back and kind of show you what happened. I'll just reopen this. So what happens when we make a selection and say apply modeling parameters is that Ava basically makes a connection with Facies modeling in Patrol, and it automatically configures this entire dialog ready to run. Okay, so we won't run it now because it will take a couple of minutes to run, and I don't think we've got a couple of minutes. So in the interest of time, we'll just skip that. But you'll see what I mean. So you take the depositional concept, you apply it to a 3D grid, and then you execute. It communicates with Facies modeling directly, and you can just run it in a normal way. And then, of course, if you're running workflows and things in Patrol, these settings are available to you to revisit through the workflows as well. We can come back to that point in the discussion maybe. But let's look at the results. So I'm just going to jump into a couple of different windows now. So I've just preset these because it's kind of a bit easy to see. But obviously, with this kind of setup where you have multiple depositional concepts, you have the ability to quickly test a couple of different alternative analogues. So here, for example, you're looking at the results from the humid coastal plain one, which is ours. And for those of you that do facies modelling often in Petrel, yeah, these are slightly more realistic channel geometries than you could, well, certainly more realistic than the defaults. And yeah, a little bit more, yeah, like what you see in nature, basically. So this is kind of nice. It's maybe hard to see because the cells are a bit dark, but we are tying to the well logs in this case as well. So we need to, because obviously we need to honour those the hard data points that we have. Just to look at an alternative, so this was another query that I created previously, so a different depositional concept. And in this case, I didn't check the humid option, I just used coastal plain. And you kind of see similar geometries appearing there as well. And then finally, just to kind of show you as well, as I was showing you in the Explore area, there are different scales of data inside the database. So you can obviously build queries at the depositional element scale, architectural element scale, or the facies scale. So in this particular view, I have one I made earlier from the architectural element scale. And in this particular instance, you can see, if I just zoom out slightly, again, you see the large scale channel bodies as we saw them in the depositional element scale. But here you also see the cold facies and some of the additional bank as well. So you're representing all 4 facies in this particular case. Okay, so that was a bit of a whistle-stop tour around AVA. There's a bit more to it. I'll just point out 2 things quickly back in Overclastics before we go to the summary. Just come into one of these depositional concepts, doesn't really matter which one. I just want to show you 2 elements that we're kind of evolving at the moment. So one is this grid setting area. So one of the things that we believe we should be able to do with these databases is kind of help to inform grid resolution. So we're looking at functionality that's a bit more sophisticated than what you can see on the screen, but using the element dimensions within the database to start saying, hey, if you want to capture the real heterogeneity that you see laterally and vertically, you need to be thinking of a cell size like this. So this is one of the things that we're evolving in the coming months. And another option, which kind of looks a bit blank at the moment, but for those of you that kind of Petrel heads and use this thing called MIPS, model input parameters, we are providing an option where you can add the MIPS information directly into the depositional concept and then compare it with the intelligent defaults that we provide in Overclastics. So I think that's kind of interesting as well. So there are a couple of areas that we're working on separately. And of course, on top of that, we're looking at things like new algorithms and doing more work on other databases, etc. So what I think I will do is let's just run another poll quickly, Laura, and then we'll summarize. So there's another poll, which is basically, as I mentioned, there's a few different areas. We've got lots and lots of ideas. Lots of ideas coming from companies as well that we talk to about what they'd like to see us do with these databases. So just run a quick poll now to kind of get your thoughts on, what do you think basically? What should we focus on next? And when everyone's had a chance to vote, then Laura will share the results.
So the result of the poll shows that a third of participants believe that additional databases should be the focus of our work next, while the rest of the participants believe that well log comparison against existing databases is where we should focus our efforts in the future.
Interesting. Okay, and that's quite similar to what we heard in this morning's session, actually. So, yeah, there's additional databases, certainly an interesting one. There are more databases out there than just the Leeds ones in the public domain, and also internally in companies as well. So quite a few of the companies we talk to do have proprietary databases that we're now looking to include alongside the leads ones in Avoclastics. The point about well log comparison, that's an area that we've been kind of prototyping, looking at quite recently actually, because clearly there's an opportunity to start comparing or compiling statistics from the well logs themselves and actually compare those directly against what we're seeing from the databases themselves. So that's certainly an area that's interesting to us going forward. So just to briefly summarise then, and then we'll jump into any questions. So for us, we feel that what we have with AVA is kind of a single point of access to some really world-class analog databases. So these databases that come from, sedimentologists at the top of their fields at Leeds. And we've tried to make them and present them in a way that's online and accessible to a broad range of geoscientists with nice charting and querying capabilities to go with them. So you can really explore those databases in an intuitive and easy way. As I mentioned, there's a whole bunch of databases, but currently we're working very hard to integrate the deep water database to complement the fluvial and shallow marine ones that we've been bringing to market recently. It is connected, or we're beginning to go down the path of connecting these databases to modelling algorithms. So you saw there that we've connected the FACS database, the fluvial one, to SIS and OBM. But there are lots of other algorithms available in Petrel, firstly, and also, secondly, in other areas as well. So one of the nice things that will do in the coming years, I suppose, is actually broaden that connection, basically. So you can use more databases to inform more algorithms in an intelligent way. One of the other things that we're going to do in the coming, well, it's a bit of a long-term ambition, but it's like one of the areas that we'd like to go next, is basically link up these kind of workflows, the one I showed you, for example, with uncertainty workflows. So there's no reason why further down the line we can't fully integrate and deliver these settings in a more structured way into uncertainty workflows. Again, in Petrel or other platforms too. And finally, just to mention, I did just highlight previously the incorporation of proprietary data, but we basically have built a system that's very customizable at a company level. So if companies have their own databases, for example, so some companies have deep water and fluvial databases of their own, they've asked whether they can integrate them into our system. The answer is yes. That was always the ambition when we set out to build Avoclastics. And on top of that, a couple of companies have come to us and said, well, hey, we actually have our own Facies modeling algorithms that we've developed in-house. Are you able to connect to those and inform those with the databases? Again, the answer is yes. We foresaw this, so we have a system in place for doing that. And actually the logic itself, so the way that we convert the analog information into the inputs for the Facies modeling algorithms, that logic is also customizable as well. But again, that's done on a company level. So we've tried to make the system as flexible as possible in that regard. So I guess on that note, I'll hand it to Laura and she will kind of field or ask me questions, I think. So go ahead, Laura.
Thank you, Vicky, for taking the time to introduce us to the use of analogues in geomodelling using Avoclastics. We'll go ahead and start the questions and discussions now. And just a quick reminder that there's two ways you can ask questions in this session. You can use the question box in your control panel and type your question there, and I'll read them out to the webinar. Or instead, you can pick the raise your hand option, and we can take your question verbally instead as well. So if you have any questions, please feel free to ask them now. It seems, Vicky, we have a question about DMAX. And you mentioned earlier in the talk that we are looking to integrate DMAX, and one of our attendees is wondering how soon that'll be happening.
I did. So yeah, indeed, we are going through the process currently of integrating the deep marine database, or deep water database. Keep getting told off because there's lakes in there too. So the deep water database is being integrated currently and will be released before the end of the year in AVA. If you do want to have a look at that data though, do feel free to drop me a note and we can set up a session because we are offering previews of that data to companies on request. So if you want to see what we're doing with DMAX, please give me a shout.
Thanks, Vicky. We have another question related to customization options that you discussed a little bit about already, but could you expand a little bit more on that?
Yeah, so I guess, so there's basically 3 ways that we customize AVA. So as I mentioned, you can add additional databases, and they can be proprietary databases if companies have them. Secondly, we can integrate with modeling algorithms that are outside of the normal ones that people have available to them in Petrel, for example. So some companies do have their own Facies modeling algorithms that they've implemented as custom algorithms. We can work with companies to connect our databases up to those. And again, the logic that can be customized as well. So the way we translate the data in the depositional concept from the query of the database to the inputs for Facies modeling algorithms. I guess one point I would make about the integration of proprietary data. So this is quite an interesting and challenging area for us, and we're working with a couple of clients actively on it right now. So quite a few companies do have some form of proprietary database that they've been using in-house in some cases for many years, to help them support their workflows with analogues that they have identified. And one of the interesting challenges is the structure of those databases relative to the structure of the leads databases that we have access to. And what we're finding is that there's a lot of discussion about nomenclature. So we have to always go through an exercise with these companies of saying, well, what do you mean by a laterally accreting macroform in a fluvial system, for example? So there's some quite fun geological discussion, but essentially it's a mapping exercise between the database structure from the client's proprietary database and the leads one. And so far we've managed to overcome that barrier and actually match those up successfully. But yeah, that's a topic I could talk about for ages, but I'll leave it there for the moment.
And someone's asking a question, Vicky, about if they wish to trial AVA Classics, how do they go about that?
Yep, so if you want to give it a try, then you can drop me an email, and I'll display my email on the screen in just a second. And what we'll do is we'll probably set up a quick session with yourself and potentially a couple of your colleagues as well, just to give you a bit of a longer demo, so you can see a few more of the features as well, maybe look at the other databases a little bit. And then following that, we'll give you access to our online environment. So we have an online evaluation environment, which is very easy to use. We have our own Petrel licenses on there, and you can just kind of log in remotely from your desktop. I believe you can even do it from your phone, but you can certainly do it from your PC or your laptop. Just log in remotely through an internet connection and just look in our virtual environment and have a play around with a test project and actually kind of use it without us sort of looking over your shoulder to get a better feel of how to do it. So yeah, as I say, I'll put my email on the screen in a minute. If you're interested in that, just give me a shout.
And it seems we have one final question, Vicky. And an eagle eye attendee noticed whilst you had Petrel open that you had some other AVA tabs open as well, and they wanted a little more information about what that was all about.
Yep, so we have 3 AVA products currently. 2 are in the market and 1 is not currently, but it will be soon. So AVA Classics you've seen a little sneak peek of today. AVA Saturation we brought out a couple of months ago. We're expanding at the moment, and that's basically to address or provide support for the saturation modeling workflow that people try and undertake. So saturation modeling is one of those weird topics that gets lost between the geologist, the petrophysicist, and the reservoir engineer. And what we wanted to do was kind of provide a supportive workflow that allows you to derive saturation height functions currently from log data, but eventually from core data too, and actually apply those saturation height functions in a really structured way to 3D grids. So that's the problem we've solved there. And we've actually got a webinar coming up on that in a month or so if people are keen to hear more. AVA Structure was the 3rd one. That's currently not available yet. That's still in development, and we'll be launching that next year. But that is basically a technology we are developing which allows you to look at, well, structural uncertainty as a general topic. So the seismic structural uncertainty, and the problem that is designed to solve is how do we go about quickly creating multiple plausible structural realizations that can be carried through the reservoir modeling workflow. So rather than being anchored on a single structural framework, this technology is allowed to come in the pre-model space and get up there ahead of time and help you develop a couple of different alternative plausible structural frameworks that you can take straight through. We are actually looking for clients to work with on that particular product, to do early market engagement with. So if you have a particular interest in structural geology and like to know more, please give me a shout, because we're actively looking for people to collaborate with on this particular tool.
Excellent. Thank you, Vicky. It looks like we've covered all the questions that we had. So before we wrap up, Vicky, is there anything else you'd like to cover?
I don't think so. I think that's everything. Let me just put my email on the screen as I just promised. So yeah, if anyone wants any more information, I realise that was a quick whistle-stop tour of Clastics, but if you have any more queries and questions about the databases and how we're trying to use them, just drop me an email and we'll certainly set up a session. And otherwise, I'd just say thanks to everyone for joining and taking the time out of your day to participate. I really appreciate it.
Great, thank you, Vicky, and thank you to all our attendees. As Vicky just said, we really appreciate you joining our session today. Just a reminder that this webinar has been recorded and attendees should receive a copy via email within the next 24 hours. For those of you who couldn't attend the live session and would like to revisit it, or if you want to share this with your colleagues in the future, we will be putting a version of this webinar up on our website sometime soon. A final reminder that if you want to find out more about Ava Clastics, you can do so on our website. And we're displaying the website address on the screen, but I'll also read it out: www.pds.group/avaclastics. You can also join us for our next webinar, which takes place on the 18th of September, and we'll be showcasing Ava saturation. As Vicky mentioned earlier, Ava saturation allows users to rapidly run multiple scenarios to better understand saturation uncertainties that arise from using differing calculation methods. Thank you again for joining us today, and we look forward to seeing you next time.